Thanks everybody for joining the monthly MIDAS webinar. My name is Harry Hockheiser, Director of the MIDAS Center. Happy to have you here and be your host today. One of the things we've tried to do with the webinar is to get a bunch of early career folks in to talk about their work in progress. And many of these folks are either soon to be looking for new positions or definitely actively looking for new positions. And this is a time for them to get themselves out in the community and for others to learn about their work. And so in that spirit, it's a pleasure to welcome Maria Gutierrez. Maria is a final year PhD student at the University of Cambridge in the UK, where she studied mathematics undergraduate and also completed a master's degree. She's based in the Department of Applied Math and Theoretical Physics. And her PhD work is funded by a Gates Cambridge scholarship. She's going to talk to us about a topic that I think is definitely of interest to folks building models, this notion of vaccine escape. And as we all know, the COVID vaccine has definitely been characterized by a trend of early efficacy and then later decreasing efficacy. And so this is a problem that's going to be with us in terms of COVID for a while, and therefore something we'll need to take into account in our models. And so I'm really interested in hearing about the work that Maria has done on this regard. So Maria, thank you for joining us, and please take it away.
Thank you. So wait. For a few seconds, I want all of you to look at this graph and try to make sense of it. How might it be possible that as we increase the vaccination coverage, we obtain more total infections? We increase the vaccination coverage in our model, and as a result, we get more infections than what we will have without vaccination. Well, with SARS-CoV-2 in mind, many scientists worried about the potential evolutionary consequences of vaccination campaigns. And indeed, many were able to show that in some circumstances, intermediate levels of vaccinations increase the risk of escape, that we get new strains that evade the immunity that we have in the population. However, there's some caveats to their approach, so these results are not necessarily valid in all contexts or with maybe other pathogens or vaccines that are different than the ones that we were facing during the pandemic. So this is my first goal for today's talk, is whether is it actually true that intermediate vaccination levels, they always lead to the highest risk of vaccine escape, or is it possible that we get other patterns? And my second goal for today comes back to the graph that I showed earlier. Is it true that if intermediate levels of vaccinations increase the risk of escape, does that also mean that they increase the total infections that we would get? Or maybe they do not have the same result in the total infections, because obviously we all know that vaccines have incredible benefits in terms of reducing transmission. So these are my two goals for today. And obviously this is all within the topic of my PhD, which I have to thank my advisor, Julia Gog, in Cambridge. This work wouldn't be possible without her. Yeah, and the slides for this talk will be available in my website in case anyone has to leave early or wants to look at them later. And I am indeed looking for a postdoc position for next year. I'm hoping to submit in the spring. So if anyone knows of any openings for after that, I'll be grateful to hear about them. So with that, let's get back to the goals for today and the discussion that we're going to have about vaccine escape. So first, I'm going to start sharing this model that we published last year, and I think this is the backbone of my PhD research. And what I'm going to talk about today is how do we model vaccine escape in a population. And then I'm going to talk about more work that's currently in preparation that help us answer that question, those two questions that we have, whether it's always intermediate levels of vaccination that increase the risk of vaccine escape, or and whether that effect might lead to more infections overall, not just high risk of vaccine escape. I see that there's a question in the chat. Oh, yes, thank you for putting the link there. Okay, so I'm going to start with the backbone model for vaccine escape. So I'm going to take a very simplified approach. I'm not going to do any within host modeling. I'm just going to consider individuals, and I'm going to differentiate them by vaccination status. So I have unvaccinated and vaccinated. And then we can think that the more infections that we have, then the more likely there is there's a mutation, and that mutation leads to an escape strain, like maybe Omicron was to some extent escaping the population immunity. But the key idea here is that we have two types of hosts, vaccinated and unvaccinated, and there might be different levels of selection in unvaccinated individuals or vaccinated individuals. So with previous models, yes, grouped together all the infections, here I'm differentiating the two groups, and I'm including this parameter here that's called theta, and that's going to be a key parameter that's going to appear throughout this talk and throughout my models, that it weights the relative selection in vaccinated hosts compared to unvaccinated individuals. So that regulates whether selection mostly comes from vaccinated individuals or unvaccinated. And a question that I like to ask people when I explain my research is whether they expect vaccinated individuals to contribute more to selection towards vaccine escape than unvaccinated individuals. So we're assuming that both, so suppose you have two individuals and they both get infected, one is unvaccinated and the other is vaccinated, then with whom of them are you more worried that that they might lead to a mutation that generates and the next variant of concern maybe for COVID? And people tend to say that it's vaccinated individuals because there's selection for those escape strains in them, and that is true. As we increase the immunity in the host, and there's more selection towards this escape mutation, so they are more likely to be transmitted onwards to other hosts. However, on the other hand, from classical phylogenomic thinking, we know that there's going to be less mutations that occur in infections in vaccinated hosts. And this is because the immunity from vaccination leads to lower total viral load. In the case of COVID, it might be more in terms of faster clearance. So there's overall less time for the virus to mutate. But if that mutation that happened, then it's going to be selected more in a vaccinated individual. So we do need to balance those two factors. And it's, I think, unclear, in my opinion, at least for COVID, which of the two hosts contribute more. So if it was vaccinated individuals contributing more to the escape pressure that might be here, then this parameter theta will be greater than 1. Indeed, if theta was really, really large, it will only be infections in the vaccinated that are driving vaccine escape. Whereas on the other hand, if theta is 0, then it's only infections in the unvaccinated that might generate these escape strains. And the papers that I showed earlier, they were just working with only the vaccinated, only the unvaccinated, or just adding the two of them together without really studying the effect of this parameter. And that's the key theme in my work, that is I don't want to specify this parameter because I think we don't really know what it is, and it might be different for different vaccines or for future pandemics. So now that we have that formula for the escape pressure, now we need to actually find it. And for that, I use classical compartmental models, SIR models. And the only difference with the standard SIR model is that here I'm distinguishing unvaccinated individuals, unvaccinated individuals. I have them in different parallel compartments. And an important modeling assumption that I make is that vaccination here happens before the outbreak. So obviously this is not entirely realistic, but you might think of this as okay, we've given some vaccines and then we have a new epidemic wave coming now with a new variant. How does the vaccination coverage, so the amount of people that we vaccinated before the wave, how does it affect the evolutionary potential in the new epidemic wave that we're getting? And so we do that with this model. So the important parameter here is C, which is the vaccination coverage. And of course, how I'm modeling vaccine immunity is also important. So I want to consider two possible effects that vaccines have. One here is reducing the susceptibility of a host. So this is this protection against infection. And then there's also reduced transmissibility. Obviously, there's other important effects from vaccination in terms of like hospitalization and disease outcomes, but those are not important for the epidemic dynamics, which is what I want to calculate here. And if you read our paper, then we also do a different endemic scenario. So if you're interested more in an endemic disease, then you can look at the results that we get for that case. But here with this SAR model, we can actually like do a lot of analytical work to find the final size solution in a similar spirit as with traditional SAR models. And so we can find the cumulative escape pressure, so integrated across the whole epidemic wave. And this will depend on the initial vaccination coverage that we had. So we can compare if we have had this level of vaccination versus we have had more or less vaccines given out, how does it change the probability that we got an escape strain? And this is the expression that we get. It looks a bit scary, but this part here, it's proportional to the final size. It has the Lambert W function, which also appears in the usual final size solution that it's often given in terms of like implicit equation. But the key part here is this factor here, which is the escape blocking factor, because it has theta S, which is the vaccine protection against infection. But crucially, it has theta E, which is this parameter that I mentioned earlier that we don't know its value. We don't know whether it's lower than 1 or larger than 1. And so that's going to determine a lot of how the vaccination coverage affects the escape pressure. Because in front of this factor, we have the vaccination coverage here. And so the sign of this factor that could be like negative or could be positive, that's going to determine a lot how vaccination affects the cumulative escape pressure. So these are the results for the escape pressure if we actually plot it. And as I said, this parameter theta E is really important. So if theta E is high, that means that it's mostly the infections in the vaccinated that drive vaccine escape. Then we get this unimodal shape where intermediate vaccination levels are indeed the ones that maximize the escape risk. And this is similar to what others have found before. However, if theta E is low, like not necessarily below 1, but just like not super high, then the escape pressure is decreasing. And what that means is that, well, if vaccinated individuals maybe only slightly contribute to selection a bit more than the unvaccinated, or if they contribute less than the unvaccinated, then vaccinating is always good because we reduce transmission a lot. So that's less infection. So that's fewer opportunities for mutations of escape strains to appear. So in that case, we do not have that peak at intermediate vaccination levels. Okay, so that was the backbone of the model, but now there's a lot of questions that you might ask, and looking at how simple my model it was, there's a lot of caveats. So the first one that I want to address is, what about partial immunity? So immunity that you obtain from an infection. And so in my previous model, it was just a standard SAR structure, so that if you recover, then you never get infected again. Whereas here, I will modify the model so that it's only partial immunity, just like with the vaccines, that you could be vaccinated but still get infected. And same for COVID, you can recover, but you might still get infected even with the same strain. And the biological motivation for studying reinfections in this context of vaccine escape is that the same evolutionary argument, the same phylogenetic argument, can also be applied to hosts that have immunity from a past infection. Because that immunity, if they get infected again, that might also increase selection for escape strains. So instead of just having vaccinated individuals like we had here in front or like behind this theta E parameter, in this new model, we have naive hosts and hosts with partial immunity. But it's the same thing, and it's this parameter that measures the relative selection in partially immune hosts, and we don't know the value of this parameter. So here I'm just grouping together all vaccinated hosts that get infected, might be the first infection or second infection, and also reinfections in unvaccinated individuals. Although, of course, in general, like we could split all four groups, but for now, just stick with this. So I have this theoretical expression for the escape pressure, but we again need to calculate it using the SER model. And just to clarify how I'm doing this approach is that after infection, there's a probability that you have protection and so you fully recover, or you might be still susceptible, like fully susceptible. And so that's determined by this probability phi s. That's analogous to the vaccine protection, but I'm not assuming that they are the same because in general, it might be that vaccine protection is stronger than infection immunity or vice versa. And I know this model might be like completely standard because, well, if I had done a normal SARS model, then I would get with waning immunity, then I would get an endemic equilibrium. And that's actually one of the cases that we covered before in the paper. So I was interested here in having a model with partial immunity, but that still lead to a transient epidemic wave. And so we have this transient epidemic wave, and I'm not going to go through the mathematical details here, but we can still integrate the final sites and find the infections in all groups. So like naive individuals, reinfections in unvaccinated, and then vaccinated infections in vaccinated individuals, both first infections or reinfections. Okay, so the finding here is that a different overall behavior is possible if reinfections are likely. And in particular, the escape pressure depends on the relative protection from vaccines versus infections. So that's why I wanted to have a separate immunity parameter, one from the protection that you get from the vaccines, and then one that the protection that you might get from an infection if you recover. So the first possibility is that vaccines are less protective than infections. So a limit case of this scenario would be the previous model where infections were fully protective, like you could not get reinfected again, so it was full immunity. And so that would be a specific case of the general Murray scenario where the vaccines are less effective than what we would call natural immunity. And in this case, we get the same result that we had before, where it all depends on theta e. And it makes sense that we get the same result because, well, it was like a limit case of that. And yes, it's the same result. But if we do change the relative protection from vaccines so that it is stronger than the protection that you get from infection, and this might actually be true for some vaccines or for some pathogens. I'm not saying that it was the case with any particular COVID variant or COVID vaccine, but it could be the case if we had like really good vaccines. And then here the results is actually quite different. So it doesn't matter what theta e is, the risk of escape is always decreasing. And we can try to think for a bit why this is true. And how I try to understand it is to think, well, if vaccines give you more protection than infection, even if they increase the risk of escape in each individual infection that happens in a vaccinated individuals, that increased risk would also be happening in an individual that gets reinfected. And for the epidemic wave to come to an end, like we need to build herd immunity. And immunity is what's driving escape, but it's kind of more effective to drive it through vaccination than to drive it through infections. And so you get less chances of mutations if you vaccinate more, because the vaccines are more protective. And obviously they also, vaccination also reduces the overall number of infections, so it's all good. So this is like a clear example of like the unimodal result where intermediate vaccination levels are the worst. Like that's not necessarily true in this case. And so I think this result is important to obviously we need to be worried about vaccine escape, and I'll keep talking about it for the next 20 minutes. But this is an example of vaccines are not going to make everything worse necessarily. But then another related topic that or concern that I want to address is what happens in infections in vulnerable hosts. And in particular, it's honestly like a big hypothesis for how Omicron emerged or its origin and after other variants of concern from COVID is that they came from chronic infections in immunocompromised hosts. So these really long infections that allowed the virus to mutate a lot and then generate a different genome, well, not different genome, but a lot of substitutions that led to variants like Omicron with escape potential and similar to other variants. And so just like we were thinking, okay, maybe vaccinated individuals contribute more to selection, then it might be independently of vaccination or status, it might be true that some hosts, like vulnerable immunocompromised, contribute more to selection. And so to address this, I split my population in two groups. So it would be the vulnerable hosts and the healthy hosts, or immunocompromised hosts and healthy hosts. And I still have vaccination. So overall, there's like 4 different groups. But the key idea here is that I introduce another factor that I'm calling alpha here, and that's the relative selection in immunocompromised hosts. So alpha is greater than 1. That means that it's an infection in an immunocompromised host is alpha times more likely to generate escape strain compared to infection in a healthy host. And again, I want to study the effect of vaccine. So I'm still splitting the population in the 2 groups, vaccinated and unvaccinated. So that's why I have 4 groups there. And I still have the theta E parameter there for infections in the vaccination in both groups. But the key thing here is alpha that's weighting infections in the immunocompromised. And so again, I'm going to go through the mathematical detail, but we can also include some more population heterogeneity. So you could think that the healthy hosts are maybe younger hosts, and that maybe they have a slightly higher contact rate here. So this is taken from previous paper that my supervisor had published as vaccination campaigns were starting, where you try to understand the effect of different vaccination strategies on this escape pressure. So just assuming a very simple contact matrix with you have an increased contact rate for the healthy host. And then the key addition here that I make to this model is that the immunocompromised hosts contribute more to escape through the parameter alpha that I mentioned earlier. And so we have different vaccination coverages for each group. The escape pressure obviously depends on the vaccination coverage on each of the groups. But I'm going to study its effect as a function of the total vaccine coverage. But I'm going to explore 2 scenarios. One where you vaccinate first the vulnerable host and then the healthy host, and the other one you start with the healthy host and then with the immunocompromised and vulnerable host. And the motivation for starting with the healthy host is that for some models and in some situations, it actually makes more sense to reduce overall mortality, to just focus on the host with a lot of contacts. If they're driving a lot of the transmission, that might actually be the most effective, even to protect the vulnerable. And yeah, this we showed on that paper. So I want to compare the 2 vaccination strategies and see what's their effect on escape pressure. And I'm not showing here I'm not showing really the actual mathematical model or the solving of it, but still we can have a final size solution for the epidemic wave, having the population split in different groups. So the escape pressure, and I'm focusing at high theta E, so that's when in the original model we got that unimodal shape. But the escape pressure depends on the vaccination strategy. So if you start first with the immunocompromised or vulnerable older hosts that contribute more to within host selection, then you get the same shape. You have that peak when you've basically vaccinated all of the vulnerable hosts, but as you start vaccinated the healthy hosts, then it decreases again. But then if you switch the order and you start first with the healthy hosts and then that have more contacts, so that's going to be good to reduce transmission, but not necessarily to reduce the escape pressure. But yeah, to be precise, you get this bimodal shape at high TDI. So you can think of this as like having a local maximum here where you are like at intermediate coverage of the healthy population, and you have another local maximum at intermediate coverage of the vulnerable. But you get a local minimum here as you switch from vaccinating one population to the other. And the reason why I think this shape is kind of interesting for vaccination strategies, and to be clear, I'm not advocating that we should use this vaccination strategy of vaccinating younger people first. But if it was true that this was a good idea, then from an evolutionary point of view, then we could say, well, we're just gonna vaccinate a lot until we get until this point, intermediate point, not just stop at that peak, just get to the intermediate point, and then if we actually have more vaccines to continue, then do the second part later, rather than get stuck on a local maximum for the escape pressure. And again, this is just another example that it's not always intermediate levels that maximize the risk of escape, intermediate vaccination levels. So just to recap, for now, the possible shapes of the escape pressure, we first saw that relative host selection is key. So that's why this parameter theta is really important. It's not always peak at intermediate vaccination levels. And the relative protection from infections versus vaccines, that also matters, because we saw here an example where with really protective vaccines, then the escape pressure is always decreasing. And finally, the last example that I just talked about is that if you include population heterogeneity, especially immunocompromised hosts, then it matters a lot in which order you vaccinate the population. Okay, so now slightly different angle here. I'm gonna go back to just using the background model, so no population heterogeneity and no reinfections with the same strain, but I'm going to study how a new potential mutant escape strain might spread. And specifically, I'm looking at this phase of stochastic emergence. So it's this initial phase where maybe we have one individual that has generated the mutant and is trying to spread it to other hosts. But because there are so few infections with the mutant, then the stochastic effects are really important, and the mutant might actually go stochastically extinct, even if it has an R number greater than 1. And so for the escape pressure, for a second, I'm going to stop talking about the cumulative escape pressure across the whole epidemic wave and just look at the escape pressure rate at any point in time. So I have the same expression that I had before with the infections in unvaccinated and vaccinated weighted by theta E. But the key thing here is that I am multiplying it by the emergence probability that a mutant that appears at that time t, that it survives, well, quote, survives a stochastic extinction, so it's able to emerge. And well, I'm not modeling the I guess longer term invasion dynamics. I'm not looking about like coexistence or replacement of the original strain. I'm just looking at the probability that it moves on to this phase of exponential growth and survives to this early spread phase. So to calculate that probability, we need a bunch of ingredients. And the important, and another important assumption is that I'm assuming that the spread of the mutant does not affect the epidemic dynamics of the wild type strain. But of course, the epidemic dynamics of the wild type strain are going to be really important for the mutant because they are going to change the number of susceptible hosts that the mutant might infect. And to actually calculate the number of susceptible hosts, the cross immunity that hosts that are immune to the wild type is really important. So if this cross immunity is high, then very few hosts that are immune to the wild type are going to be susceptible to the mutant. But if it's low, then there's the opportunity that hosts that were immune to the wild type, either from vaccination or from infection, then they might be susceptible to the mutant. And so that would be the case of an actual escape strain that it's able to spread. But to quantify, or like to really measure the probability that it is able to spread, we need the effective reproduction number of the mutant. And with that, we can calculate the emergence probability. And many of you will be familiar with traditional branching process theory and a lot of like classical approaches with a bunch of assumptions about the transmission process that leads to this really neat formula for the emergence probability that just involves the effective reproduction number of the mutant at the time at which it appears. However, that formula, that approach, is not really valid here because that approach neglects susceptible depletion, and it's okay to ignore susceptible depletion due to the spread of the mutant, because there's so a few infections with the new strain that it doesn't really make a substantial difference. But you have to remember that here the wild type strain, it's still spreading through the population, and it's taking away susceptible hosts that might otherwise be infected with the mutant, and it's also adding some partially immune hosts that are immune to the wild type but might be susceptible to the mutant strain. So that overall means that the transmission rate of the mutant changes in time even through this like really short phase of stochastic emergence. And so we have to modify the standard branching process, like Berthel's branching process, and still use a time homogeneous branching process with specifically a time-dependent transmission rate, which is just the R number. And obviously, I'm not going through the derivation here, but you can get to this ordinary differential equation for the probability of emergence that has the R number there, and that depends on time. So obviously you cannot solve this very easily, but there's been a recent preprint with a similar approach, and a few other. This approach has also been used in other contexts with like emergence in periodic environments, maybe due to like seasonality or other kind of time-dependent effects that affect the spread of or like the emergence of a new outbreak. And so I'm adapting this approach here to the emergence of a new strain where the susceptible pool changes due to the wild type. And so we can find analytically this probability, although it's a bit complicated and depends on the transmission rate, or you can just solve it numerically. And then we will find how at each, like the time at which a mutant appears, that's really important for the probability of emergence, and that overall affects the cumulative escape pressure. And just going back to the cumulative escape pressure, which is what I had been talking about before the rest of the talk, it's kind of intuitive that the cross immunity is important. Cross immunity between the strains is important, because if you have high cross immunity, that means that the mutant doesn't have much of an escape advantage, because it cannot infect many of the hosts that the wild type will not. So in that sense, then it makes sense that because there's, I'm going to start with low cross immunity. If there's low cross immunity, then there's a high emergence probability, and so it can infect a lot of the hosts that the wild type could not. So these effects from the stochastic extension, they're not really important, and so we get the same thing that we had before. Like appearance is the most important. The key thing is that we get enough infections and enough selection with theta E so that the mutant can appear. But if we had high cross immunity, there's a low emergence probability. So then the calculation that we had before, it doesn't really check out, because if the little p, the emergence probability is going to be small, then the escape pressure, it might be small or zero actually for like a few of the times that we were using before to integrate the escape pressure. So that's why the shape of the cumulative escape pressure changes compared to what we had before, where we were not including this phase of stochastic emergence. And so if we have high cross immunity, then a new shape is possible, and strain appearance is quite likely, but it's the emergence of that strain what limits evolution. So what's important from the pathogen's point of view is not that it gets many more mutants, but that those mutants are able to emerge. And so we have this new shape as a function of the vaccination coverage, and it's different, and it happens regardless of theta e. So theta e, I did not plot it here, but it would just show like a slightly like lower curve, but the same kind of qualitative behavior. And so we have this local minimum at like low to intermediate vaccination coverage, and then a local maximum at intermediate to high vaccination coverages. And it's a bit hard to understand why exactly we have this shape. Like it makes sense that it's going to be different, but it's a bit hard to understand why it's exactly this shape. I have some hypotheses for why it is like that. So if you're interested, feel free to ask me about that later. But just to recap, I had shown that it's not always intermediate vaccination levels that maximize the risk of escape. We had two scenarios where we had like two different possible behaviors. And if we add in a stochastic emergence with high strain cross immunity, then we get a different shape. And so that answers the first goal that we had for today. So remember, I had asked, is it always true that intermediate vaccination levels lead to the highest risk of escape? And sometimes yes, so that would be the green curve here with high theta e. But in all the other cases that we have here, no. So there's a lot of factors at play. So now moving on to the second goal, even if it's true that intermediate levels of vaccination increase the escape pressure and the risk of escape, do they result in more infections in total? So that's the final part, is the impact of the escape strain. And there's many approaches that one could take here to model the impact of the escape strain. So I'm going to take a slightly different approach to what I was doing on the previous part of the talk, because I was assuming that a new strain emerged during the epidemic of the wild type. But here I'm just going to assume that a new strain has emerged and it's spreading after the epidemic of the wild type has ended, so not overlapping epidemic waves. And the reason for that is that I'm going to use the cumulative escape pressure over the first wave to determine the cross immunity between the two strains. So on the previous part of this talk, I said that the cross immunity was really important for stochastic emergence, but it was just another parameter in my model, and I could play around with this value, and we found that depending on the cross immunity, we got different outputs for the escape pressure. But here, it's not on this slide, but I promise you will see how the cross immunity depends on the escape pressure that we have on the first epidemic wave. So to do that, I borrowed the approach from the influenza literature and assumed that the antigenic distance between the strains, so that's like how different they are in terms of their immune effects, receptors, and so on, epitopes, that the antigenic distance depends on the escape pressure. So the more escape pressure that there has been, the more different they are, the more antigenically distant they are. And I'm using my original cumulative escape pressure formula here. So including infections in the unvaccinated and the vaccinated, and theta e, which I said is quite important. It's embedded there. So it's escape pressure, but it might be easy to think about it. Okay, a linear combination of the infections and in unvaccinated and vaccinated. And that's the antigenic distance. And then the cross immunity decays exponentially with the antigenic distance. For the exponential shape, the details are not important here. Why would it be exponential decay? But the key idea here is that the farther away they are in antigenic space, then the less cross immunity there is between the two strains. And that makes sense. If there's like a lot of escape pressure, the antigenic distance is really large, then there's basically no cross immunity left, and the new strain can infect everyone. And so once we had the cross immunity, then we can use that to calculate the final size of the second epidemic. But just remember that it's all quite interrelated, because if we start with the revaccination coverage, which is really the main variable in our model, that affects the escape pressure, and so in turn the antigenic distance and the cross immunity. The vaccination coverage also affects the first size of the epidemic, the final size of the first epidemic, and that's going to determine how many hosts remain susceptible after the first epidemic. And together with the cross immunity, that's going to be the effective reproduction number of the mutant, because that's going to tell us how many of those susceptible hosts can they be infected with a mutant strain, either because the cross immunity was not effective on them or because they were never immune in the first place. And once we have that R number, then we can use standard SAR model to find the final size of the second epidemic. So I'm not showing the math here, but it's really simple SAR model again for the second epidemic once we have its R number. And so we can add together the total number of infections. So now it's not escape pressure, it's number of infections as a function of the vaccination coverage. And we have the two waves. Obviously, the first wave, I didn't really show it, but it's kind of a standard or intuitive that if you increase vaccination, you reduce the number of infections in the first wave because there are no evolutionary effects. But for the second wave, it's a bit more complicated. So the second wave is this gray curve here. If they're very low vaccination coverage, the second wave is not possible at all because the escape strain does not have any advantage compared to the mutant, or has like really little advantage that it will go extinct, it cannot spread. However, at like larger vaccination coverage, a second wave is possible. If the vaccination coverage is really, really high, then you're close to herd immunity, and then it's slow again. But at those like intermediate to high vaccination levels, that's when you get the peak of infections in the second wave. But we care about total infections, so to acknowledge if you want to acknowledge the positive effect of vaccinations on the first wave, then we need to add the number of infections in the two waves together, and that's this purple curve here. That's initially decreasing with vaccination because that's the first wave only, and then once the second wave becomes possible, then we have this local minimum here, we had another local maximum, and then it comes down again. So this is a new shape for the cumulative number of infections. And yeah, there's caveats that obviously you can get slightly different things if you tune in differently the parameters, but I want you to think of this as like a proof of concept that, okay, it might actually be true that like on a mechanistic wave that a mechanistic form that we get more overall infections as a result of the escape pressure that are generated from vaccines at some vaccination coverages. So to summarize, like, yes, it might be true that escape risk and the number of total infections, that they might be highest at intermediate vaccination coverages. And just to clarify, in this purple plot here, I'm assuming that theta E is high, just because the other example where theta E is low, it would be really uninteresting, because if the escape pressure decreases, then that's not gonna lead to like more escape risk. So it's nothing's interesting is gonna happen. But I just want you all to remember this example where it might actually be true that some vaccination coverage increase the total infections relative to no vaccination. Others might lead to lower total infections. And so that's the second goal for today. Yes, it might be true that the risk of vaccine escape results in more infections in total at intermediate vaccination levels, but we should aim to find a reasonable trade-off, and we can use modeling to explore these evolutionary effects together with the standard epidemiological effects of vaccination, and we should be mindful of that when designing vaccination strategies. And with that, thank you.
Great, thank you. Very interesting. We definitely have some time for some questions. So if anybody has any questions, please raise your hand or put something in the Q&A. I'm going to start off with something here just to hopefully prompt others to jump in. I mean, this is all really interesting sort of theoretical models and a lot to chew on here. And I have to give this a lot of thought to really make sure I really really get it. But are there any prospects for, say, looking back at COVID and trying to validate these models or apply the models to what actually happened and to estimate some of these parameters?
So I think there's two angles to you could try to do that. One is like, okay, we have enough clinical data to try to measure like this, especially this theta E parameter, like biologically, like what is it? And I think that I'm starting to see more papers in that direction. Like obviously it's not the work that as a modeler, that at least not the work that I'm doing right now, or I don't have the data to do that. But I'm starting to see more of a trend in that direction, and maybe I won't share my opinion publicly of like what I actually think this parameter it is, but I'm starting to see like, okay, maybe for this vaccine, like it might be this or that, but nothing to be confident of, but I'm getting an idea. And with is to actually like validate the model, I think it should be like kind of possible to like kind of reverse engineer it and try to like, if you measure overall like genomic diversity on different populations and you plotted them as a function of their vaccination coverage, to try to maybe fit my curves to that data. But I think the problem is that the background in population immunity is so heterogeneous from like different vaccines and infection histories, that because we don't know, at least yet, the exact like evolutionary contribution from each specific type of immune status, it would be really hard to like to have that not influence the fitting of the model to anything that we might see, I think.
Yeah, absolutely. Anything you would have to do would have to have some pretty strong assumptions, I would think. But just to get some idea of that, or even I'm sort of curious as to what your definition of intermediate levels of vaccination are, because that's a whole other parameter.
Yeah, I guess I was just trying to be very vague and be like, okay, like something like, and it's actually related to the question that's in the chat that I'll answer now. But yeah, it's just trying to say like, okay, I'm not specifying a specific like actually the epidemiological values that I didn't talk about, like the ones that I saw, but I think this is more like, okay, for a reasonable range of parameters, is it theoretically possible that we have these scenarios, or are we like just paranoid about something that's never going to happen? And I think this shows that, okay, it might happen, even though obviously there's a bunch of assumptions in my model. And one of that is what will happen if the vaccination coverage is 100%. And I think implicitly on this model, I was showing some parameters such that herd immunity is possible with like really high vaccination coverage. So I think maybe here, like, herd immunity was like a 90%, and it's there were like, okay, there's no first wave, there's no infections. But obviously I do have explored different ranges of scenarios where even if you vaccinate 100% and you vaccinate 100% and you still don't have herd immunity, so you can still get infections. And so to like summarize it briefly, it's just like the same shape that I had, but you just cut it like before reaching that end there. And so it's still intermediate vaccination levels that give rise to that. Obviously, if you have like extremely ineffective vaccines, even if you vaccinate everyone, like, okay, that could be like really bad. But I think I'm working with the assumption of like, okay, we have some vaccines that even if herd immunity is not entirely possible for some strains, like it's going to be like reasonably effective. And so that's going to drive a lot of transmission down, which reduces mutations.
Great, makes a lot of sense. Definitely not straightforward, but interesting to think about. Since there aren't any other questions in the Q&A, I'll throw out something else here that's on my mind. What about vaccine efficacy and waning? Because it seems that that's another factor that's going on here with the pressures that the individual is not going to be static in their vaccination state, but rather have a differing profile, which is going to change your parameters over time. Have you given any thought to what that would look like? And that's, I assume, going to make things a little bit more complex.
Yes. So I think it's obviously like from an epidemiological point of view, like that affects the model and that affects everything. But the reason why maybe I didn't do it straight away is that there's also an evolutionary argument that infections in individual with waned immunity like might also be a different type of evolutionary pressure. Like it might be true that okay, if you're vaccinated, you have such high immunity that you are really unlikely to give rise to escape strains, just hypothetically. But if that infection partially wanes and you can get infected, then you might be at that intermediate point where you have enough immunity to select for escape strains, but not enough immunity to prevent them to appear in the first place. So you have to factor them as well evolutionarily. But when I have looked a bit, it's not on the paper, but it's gonna be like an appendix of my thesis, basically, where like, okay, vaccine immunity wanes, so how does the waning rate affect this shape that we're getting? And so far my results just point like, okay, it's like a lower threshold for this like unimodal behavior, but it doesn't lead to like different kind of patterns.
And I guess it's sort of a similar question here, put come up in the chat. What happens to the modification parameter when vaccination is imperfect? And similar kind of an answer, I would assume.
Well, I think I'm actually like assuming imperfect vaccination here. But I guess at least the equations that I solved, it was polarized protection against infection. And then, so that means you're vaccinated, you have a certain chance of having full immunity or being fully susceptible. And then if you are in that fully susceptible, you still are less infections if you do get infected. But I did also consider for the model that is published, is actually on the paper as well, the case with leaky vaccines, where it just like lower susceptibility rate if you're vaccinated, and it does not change the results because it's the same thinking that vaccines just means lower infections, so reducing transmission reduces potential for spread. But I think that question just points to a more general theme of like, okay, are we gonna be like really picky about the vaccines? What if we have two doses or different types of vaccines? Or you know, and waning is like so complicated that it's not just like, oh, it's suddenly wane, like it's more like a continuous, and obviously like I don't even have enough data to know what this like evolutionary thing looks like with a really simple assumptions for the vaccines that yeah, it might vary a lot.
Right, which raises a whole other question, which also I'm sure doesn't have a straightforward answer, is what is this? What are the implications for policy settings here? It seems like it's hard to draw any specific conclusions
Yeah,
that
I
guide
think
vaccination policy.
I think like it would depend like what type of pathogen, like what kind of data would be available. But like look into like, a future pandemic, maybe it might be like, okay, from the beginning, we need to be ready with the like tools and like clinical studies to monitor early on
Mhm.
what does this new pathogen look like from an evolutionary point of view, and then if obviously maybe not just my models, but like other similar models that have been used in the space, if we do have the right data, then we can fine tune them and give them some insights into how different vaccination strategies might be like from this like evolutionary point of view. Or it might be like, okay, this type of populations, they are the ones that are more likely to give rise to this strain. So if we have a budget for genomic surveillance, we need to focus our efforts on this type of populations, like maybe populations with intermediate vaccination coverages, or maybe populations with a lot of vulnerable immunocompromised hosts. And because if those strains are more likely to appear in those populations, then we do want to catch them early.
Makes perfect sense. Other questions? I'm not seeing anything else here, and we really are just about at the top of the hour. So I think that's probably a good time to wrap up. Thank you, Maria, for presenting on a topic we haven't heard too much about in the MIDAS webinar series. So it was a great addition. Really appreciate your talk and the time, and I wish you luck with the completion of the PhD and your hunt for the next thing. So it's an interesting time, I'm sure. So thanks, everybody, and we'll hope to see you again next
Oh
month,
yeah, just
October
one
webinar.
second.
Go.
Sorry, I think there's someone that just want me to send my email. I'm just hoping to type it before. Well, it's actually here in the bottom of the screen, but just before the meeting kind of dies. Um,
Absolutely.
oh, oh yeah, I don't think I can type, but can you type my email?
Let's see here. I will put it in the chat. Let's see here. Trying to find it. Contact. 1 second here.
Oh yes, the chat. Sorry, yes, I can type. I'll just type it. Sorry, I was being stupid.
Yeah, you can put it in the chat.
Yeah, sorry, I'm got confused with the webinar
Yeah,
setup.
no, it's okay. And I was searching around for your email. All right.
Thank you so much.
So, and if anybody has any questions or need to get in touch with the speakers at any time, you can also just send to questions@midasnetwork.us, and we'll get you in touch with people if you need to. So once again, thanks, everybody. We'll see you next month, excuse me, for the next meeting, and take care.